What's up, guys? Good evening. Hey, hi, Srinath. Good evening. Glad you could join in. Hi, Satish. Glad to see you again. What's up? How's the new week treating you guys? Quick check. Am I audible and is my screen readable? Awesome. Can somebody please give me the OTP for today? That is the ultimate confirmation, right? No OTP? Okay. Interesting. Text recognition class. Okay. Okay, awesome. 9820, fine. Awesome, awesome. Okay, at least the OCR systems of your eyes are working. This is a good test of that. Yeah. It was well hidden today, right? I think I should do this every time. Probably try hiding it, and the first challenge is, somebody giving me the OTP. That's entirely possible. So, yeah, awesome. Cool. So, how's it going, guys? How did you find the CV lectures? And welcome to the NLP lectures now. Slowly, we're learning how to build smart systems, right? So, yeah. Hopefully, like by the end of this, we'll have enough preparation to start discussing the multimodal ways of doing things, right? So, like, based on your request, I have sort of put it through with our team, and they're okay with me generating scripts to teach things like ChatGPT, how it works, how the training works, and then talking about papers which led to ChatGPT, talking about papers which led to things like DALI and all those things, right? So basically, all OpenAI's main papers, we can sort of have a discussion on after this module ends. So, yeah, good news on that front. Apart from that, yeah, me personally, I'm learning NLP for the first time. In my bachelor's, I had done a NLP project, right? I had built a text document summarizer. So in those days, we did not have these complicated neural networks. So yeah. Oh, okay. There are people in this class who have not attended CNN lectures. Okay, okay. Sorry, guys, I didn't know that. So, those of you who don't know me, my name is Dhruv Javli. I'm basically an instructor at Scalar. I teach the math topics and the deep learning topics, right? So, the experience that I have in this field is for a year, I worked as a deep learning engineer for this startup where I helped build this network which can automatically generate images of people wearing clothes. So if you give the photo of a person and the photo of a piece of clothing, uh, essentially it generates a realistic looking image from those two photos. And apart from that, I have a PhD in signal processing and machine learning. So that's from IISc. I received my PhD recently this year. The topic of my PhD was mainly related to computer vision. So yeah, quick introduction to myself. Those of you who were not able to attend the CNL lectures and are wondering if NLP is going to be difficult, it may be because see, when we were studying computer vision, right, we came across a lot of these components. Like we learned what a convolution operation was. We learned what different types of concepts like skip connections and those kinds of things, right? So essentially, it becomes important for you to understand at a low level what these components are, right? So Amit, and people who have not attended the CNN lectures, I at least request you to watch the first three lectures where we discuss how these convolution blocks work, right? Because the convolution arithmetic is something which carries forward here as well. So we will be carrying forward some concepts from CV here, which is basically related to coding up these architectures. So yeah. Okay, some people have noticed I have a new haircut. Yeah, my mother was getting really irritated with me, so I had to get this. Yeah, cool. Deepit says we did not cover post detection in regular lectures. Could there be more such broad topics that have not been in the curriculum? So, Deepit, yes. We do have something which is known as the Advanced CV and NLP course. As a part of that, I have so far proposed 4 topics. If you have any topics which you want added, I would be more than happy to do that. Right. So, my request is if you have a topic which you would want in those set of lectures, you could let me know. So one thing that you guys want is post detection. Sure, we can talk about post detection. Specifically, there are two problems within post detection. One is the key point post detection, the other is dense pose, right? So we could talk about both of those. I had shortly introduced that when we were talking about image segmentation, right? I had talked about this amazing library which is known as Detectron 2. So that library basically has networks which do this, but yeah, it sort of merits a discussion in the sense that it would be nice to sort of go and see how dense pose works, right? Pose estimation is okay, but dense pose would be really fun, right? Yeah. So one question that I got is, when would advanced CV and NLP modules be taken after the product analytics module? So Sean, we could so we have not yet decided that, right? We have not yet decided that in terms of when it would be scheduled for you guys. Um, I need to go back and discuss. Right now, what I have done is I have conveyed to the team that people are requesting these more recent papers to be discussed, and I told them that I can sort of read these papers and explain them. So they were happy with that. Uh, so the exact dates and everything, let's work out as time progresses, right? I will let you know as the module starts, like towards the end of the module, I will let you know exactly when we will discuss this. Cool. So I got one more comment in chat. I could only complete 50% of this thing. Prasad, so people who have not finished the CV module and are wondering if you should start today, my advice would be to start. Okay, my advice would be to start because it's a good idea to sort of get a hold on to what goes into NLP, right? So the thing about NLP is it is not as mature a field as CV right now. So the first 6 lectures are not going to be that difficult in the sense that we're not going to jump into the deep learning aspects. We are going to sort of figure out how we came to these topics, right? See, to solve a problem well, it is very important to understand how the idea developed over time, right? Because it gives us a feeling of what has already been tried and tested and what should we try next, right? If you don't know what has already been tried and tested, you will keep reinventing the wheel, which is a very bad cycle to be stuck in. You will spend years before realizing, oh damn, 20 years ago some guy already saw this, it didn't work, and now I've wasted 10 years. It's a horrible feeling, right? So in general, when we learn a topic, we try our best to uh, see where the idea originated, how many people have worked on it, and what all things they've tried in the middle. So generally, when we teach a topic, that is how we go about it, and that's what you'll sort of see for the NLP module, right? Okay, so that's enough. I guess we waited long enough. I think it's about time we start. Cool. So, okay, one more comment. Okay, let me take it up. Can I get a module level note for supervised learning, unsupervised learning, MLOps, NN, and CV? Mohan, we are going to share cheat sheets, right, in each of these. So, we are in the process of making and sharing cheat sheets and summary notes. Basically, something that you can revise before an interview, right? We are going to be sharing this soon. Please stay in touch with me on Slack if in case you don't receive it over the next week. If you don't receive it, then let me know, because then I'll have to look into why it's not being done. We were supposed to do this by this Wednesday, so I'm hoping that by Wednesday it will get done. If by Wednesday you don't receive it, please let me know, right? Okay, cool. Oh, I see. So the rest you have received, right? MLOps, NN, CV you haven't received. So guys, we're still in the process of rolling it out, right? It's we're still getting it checked and stuff. So which is why Wednesday is the deadline that we have given ourselves. So if by Wednesday it doesn't happen, you have to let me know, right? Cool. Okay. So Mohan, can you please check some another one of your batchmates is telling me that supervised, unsupervised, and NN has been received, right? MLOps. Oh, sorry, NN also no. Okay, okay. For any of the modules so far? Okay, okay. I'll look into it, guys. I'll look into it. I was under the impression that and ML, NN, and this thing were the only ones left. I'll just quickly take a look. Right? Sorry. Okay, guys. Let's finally now begin. So, Chitra, it should be shared on your dashboard. It should be shared on your dashboard somewhere. Is that where you where the others found it? Aditya, Sunny? Uh, could you let Suchitra know, please, where exactly you found it? So yeah, I'll leave it to them. If not, Suchitra, please reach out to me on Slack. I'll figure this out, right? I don't have the answer ready right now. We sort of have to get discussing NLP. So let's get to the topic, guys. So everyone, I'm pretty sure, has heard of NLP thanks to the great hype that has been going on over the past few weeks, right? ChatGPT has sort of set the world on fire, right? Almost every one of us knows this word, ChatGPT. Almost everyone, right? So those of you who don't know what ChatGPT is, guys, go and check it out. Google it today. ChatGPT is one of the first generative models which is able to fool humans quite well as to whether this thing. So Turing test has been like sort of broken for this kind of a network, right? So for again some context, the Turing test is basically a test which lets us know if we are interacting with a real human or a sort of generative artificial intelligence, right? And what people believe is ChatGPT 3 and ChatGPT 4 are the first instances of actual artificial intelligence. So there are people who have done experiments with this model to sort of try and detect if it has emotions, thoughts, and things like that, right? So yeah. So essentially, broadly speaking, uh, people have believed that we have taken our first big step towards artificial general intelligence. That is basically a computer which can actually replace us. Now, a lot of questions that I get, especially over the last few weeks, the questions that I've been getting is ChatGPT going to replace me? Right? That is one of the most fundamental questions that people are asking. So, guys, ChatGPT is not going to replace you. So, I'll give you the answer which I keep giving people. ChatGPT is not going to replace you until we figure out how to verify the answers that ChatGPT gives you, right? So, unless we integrate ChatGPT with a mode which allows you to verify the answer that it's giving you, it's not going to be replaced. Why? Because at the end of the day, because humans have trained this ChatGPT, it turns out that a lot of times ChatGPT tries to guess the answer and it confidently guesses the wrong answer, right? I have seen a lot of instances of this. When it comes to code generation, it's pretty good. But again, there are limitations. You try giving it a table where you have 5 or 6 tables with complicated joins, it will not probably be able to do that, right? So there are certain limitations to what ChatGPT can and cannot get done. And what we are going to try and understand in this module, hopefully, um, is what is it exactly that it takes to build such a system, right? We are going to trace a history of all the techniques and tools that people have thought of over so many years, and we're going to try and arrive at the answer. Why did it take so long to come to this, right? Why couldn't we have done this 20 years back, right? So we're going to try and answer that question, and we're going to try and get to a point where we can use these tools more effectively if we're not interested on the tech side. And if we are interested on the tech side, we're going to try our best to understand how to build these systems, right? So with that outlook, we're going to attempt all of this. Now, one word of caution, computer vision was full of a lot of interesting and pretty amazing results, right? That's because the first great major success in computer vision came out in 2012, right? After 2012, when the ImageNet challenge was solved at a very high level, right? That is when people started taking interest in the field. They started developing new tools and techniques. So, historically speaking, natural language processing has not had so much success. Of course, natural language processing has had some success in terms of the Google search engine, right? But that is where humans stopped. Like, as long as we're able to search over corpuses of text, we were pretty happy with that solution for a long time. It took a really long time for people to actually think, what does it take to sort of build intelligence around text, right? So the word of caution that I'm giving you guys is, do not expect as great results as we've seen in the computer vision module so far in NLP, because as because of two things, right? First of all, we were pretty happy with search engines, and majority of research in NLP has been focused towards improving that. Secondly, the first thing which has come, like, now is a really good time to learn about NLP, because the first success has come now, and over the next few years, people are going to try replicating the success in different contexts. So if you guys were paying attention during the computer vision module, I told you, once object detection was solved, right? Once object classification was solved, so many things came around it, because people used to take the pre-trained model and play around with it, right? So now the same thing is probably going to happen for ChatGPT and models like ChatGPT, right? Where people are going to take these embeddings, they're going to take these pre-trained models and then build on top of that, right? So you guys, at least the people attending this particular course, have a very nice opportunity here, right? you can actually get inspired by what we were doing in computer vision, and we can try and see if we can do the same things for NLP, right? So broadly speaking, guys, what were the fun things that we saw in computer vision? The main concepts. So there are some people who have not taken the computer vision part, right? I at least want those people to know from the people who have taken it, what are the major things that we have seen in computer vision? Major concepts. So convolution, activation, pooling, perfect. So these are low level components, right? Okay, I'll make a note of this. So we began our journey into computer vision by first studying, these low level computational blocks. So let me summarize it as low level computational blocks. Right? Okay. So things like activation, pooling. Yeah. Okay. So these are conv, pooling, activations. Right? These are low level computational tools. The next one is what I have gotten in private chat from some people, and Akshay has put it very nicely in public chat. The next concept is transfer learning, right? One of the first things that we saw is if you have a pre-trained model, you can take advantage of that to do more cool stuff, right? Transfer learning is one of the key concepts that we have learned in computer vision. Okay. So we're going to see if we can do some sort of transfer learning to build cooler applications somewhere in NLP, right? We're going to keep an eye out for that. Then basically you have the base task, right? The base task. For us in computer vision, the base task was what? Image classification, right? So what we saw was once humans are able to solve the image classification problem really well, there is a nice hierarchy which is built, right? Once this becomes possible, object detection becomes possible, object localization becomes possible, segmentation, then what else? Yeah, segmentation and generation also, right? Even image generation was sort of inspired by image classification. So all of those things sort of become possible with that, right? So what we have to now ask ourselves is what is that one base task in NLP which will lead to so many cool things, right? So we're going to keep an eye out for that. Okay. Skip connections is another beautiful thing which Sumit says. Perfect, Sumit. Skip connections in architectures, right? So architectures. So we saw a bunch of cool things in architectures. We saw skip connections. We saw what else? We saw those inception modules. Yeah, 1x1 convolutions, inception module, 1x1 convolutions, etc. Right? Yeah, region of interest and aligning. So we saw a cool set of tools that we could build. Right? So we have the ROI, RPN, etc. Right? All of these things, right? Conv to D transpose, perfect. So all architecture related stuff, right? So yeah, Arun in private chat has asked me, is this somehow related to word embeddings in NLP? Yes, Arun, it is. So the two most popular the word embeddings uh, in NLP are this thing. So the older ones, before BERT came, it was this thing, right? It was word to vec, where you basically give a context of prediction. You basically want to build a network which can predict the next word, and that becomes word to vec. Sorry, word to vec is classification. Continuous, word to vec is classification. Like you basically solve a ad hoc classification task, right? So just like image classification gave us very good embeddings for images, we have these neural networks which can classify text to give us very nice embeddings. But that's not the only one. So we have a lot more cool architectures in NLP. So stuff that we're going to see new in NLP are going to be things like BERT. Then you have word to vec. We have these RNNs, recurrent neural networks. You have these LSTMs. You have these transformers, right? So we're going to slowly Yeah, sequence to sequence stuff, language translation, all of these are valid, right? So these are the new concepts that we're going to be studying with respect to deep learning in NLP, right? But for the first few lectures, like probably today and the next few lectures, we're just going to make sure our base is very strong before we go for these architectures, right? Again, I'll repeat this. It's not possible to study deep learning in isolation. People who tell you that might not be looking at it from a very long term perspective, right? In the short term, I totally agree. It's a good idea to go and learn deep learning enough to implement something. But in the long term, if you guys want to make a career out of this, if you want to be a deep learning engineer or an computer vision or an NLP engineer for a company someday, what you have to do is you have to play the long game a little bit, right? So let's talk a little bit about the long game before we go ahead, right? So, guys, the first thing you have to understand in the long game is we are in a hype market, right? Right now, as of today, NLP is getting hyped a lot. So what we have to understand is this hype is only because of that first great success, right? We should not get distracted by just that success. It's very important to build a good base in the sense that it's important to first start from concepts which are they seem kind of trivial, they seem kind of okay, this is not giving good results. The idea why we have to do those things is because we can get inspired here and apply these ideas forward in deep learning, right? So one major difference you're going to see in the NLP module versus the CV module is this one. We're going to spend a lot more time building our base. Yes, things like bag of words, things like how to vectorize a certain piece of text, right? There are a lot of skills that we have to develop. So if you're taking the long-term view on this topic, make sure you're not distracted by the hype market. The hype market will force you to go and only study deep neural networks. That's not the correct approach, right? Generic sequence problems, yes, I believe the 8th or 9th lecture. Let me quickly look at the syllabus. Yeah, so we have attention, right? So we are going to do some sort of sequence problems, right? So what we're going to mainly talk about today is the core concepts that we need before we can go and deal with the hype market, right? That's the idea. Okay, so with that out of the way, guys, it's time to start finally talking about NLP, right? So always remember, if you want to play the long term game, you have to stay committed. You have to keep practicing the basics. You have to understand the basics and then go on to more complicated things, right? If you do that, then trust me, in the long term you'll be get good with this stuff. Cool. Okay, just slight word of caution, because I see a lot of people like so there was a scalar meetup this weekend where a lot of people were very excited about chat gpt, right? They were insisting that okay, why don't we discuss chat gpt, and we did. But the problem was like what I felt was it's sort of important to build a good base before you go for that, right? So just wanted to caution you guys for that. Now it's time to move on. Cool. So let's actually start talking about natural language processing now. First of all, what is natural language processing? First of all, what is natural language? Let's start at the very basics. Natural language is the language in which we are communicating right now, right? I'm making some sounds from my throat. You guys are able to hear me. You guys inside your brains, the sound is getting converted to some concept, right? And then that concept is getting encoded as words while you reply back to me, right? This is a very nice system. I'm saying stuff, you guys are typing stuff and sending it back to me, right? But we're able to communicate seamlessly here. Although there are two different modes of communication. One is the voice, the other is the uh, words, right? So at the core of it, natural language processing is dealing with words, right? Cool. So Riju, so guys, just one moment. Riju, generally these kinds of questions people ask me in the doubt session. So I request you to please put it up as a question on the questions tab. I will answer your question, but not now, right? It will break the flow of what I'm about to teach. So I request you sincerely to put it up. No. Nothing to apologize. It's perfectly fine. We all make mistakes. Never apologize, but make sure you put questions on the questions tab. Okay, cool. So let's go ahead, guys. So now, essentially, what we're going to start talking about is natural language and why it's difficult. And no, we're going to talk about why natural language as a field, natural language processing as a field is difficult, right? Okay. So first of all, what is natural language, right? There are two aspects to it. There is the word and there are sounds. right? At the core of it, natural language processing has two components. It's multimodal to begin with. With vision, it's very simple, right? Very straightforward. We all understand pictures. We've all sort of seen pictures, so it's very easy to understand images, right? But when it comes to natural language processing, the main difficulty starts with these two components being almost interchangeable for us, right? Okay. And you will see that because of this one small thing, the way we think about words also is very, very different, right? Okay. So let's talk about this now. Okay, cool. Oh, wow. Okay. Hey, Akshay. That's okay, guy. Akshay, it's okay. Perfectly. Hey, guys, let's do one thing, okay? I'm going to actually copy this question and keep it because I don't want this person to feel like they've made a mistake. I want to answer this question, but I will answer it in the doubt session. Okay? So I request you to please stay back. Right? Okay. So let me just paste it in my notepad before we go ahead. I just want to make sure you don't feel left out. That's okay. Cool. Now, let's see. At the end of the day, how we think about representing natural languages is kind of difficult because of how we understand words and symbols, right? Okay. So broadly speaking, the way we break down text representations, right? The way we break down text representations is as follows. So let me quickly put down an image here and we'll try and understand this. Right? Okay. So let's understand this now. Cool. Sean says phonetics, phonetic words, perfect. Deepit asks me, does audio signals come under NLP? Deepit, generally no. Audio signals are studied in signal processing. There is an entire field of research which is known as speech signal processing. So audio signals on their own are studied in speech signal processing. The only field which relates these two fields, NLP and audio processing, is text to speech, right? Apart from the text to speech application, you don't need to worry at all about speech signal processing, right? So we can keep these two separate. There is enough content in NLP to stand on its own. There is no need for Alexa. You can type and you can get Google to give you answers, right? Basically, it's that. So yeah, okay. Okay, so Sean says, or speech processing part, yes, right? Conversion of speech to words, that is one aspect, but that's not the only one, right? There is the counter question. Do we have text to speech? Of course we have text to speech, right? Is that NLP? No, it's not. Again, text to speech is entirely in the speech signal processing area. It's entirely in the speech signal processing area. Okay, cool. So Riju asks me, isn't audio signal being processed before speech recognition? Recognition as diarization? Yes, it is, Riju. I completely agree with you. But here the issue is we will not study this at all in this course. Why? Because we're only going to be focused on how to deal with the words part. We're going to keep the signal processing part separate from the NLP part. Okay. So yeah, which is why I'm not going to talk about it. Right? Okay. Now let's come back to natural language processing and let's understand how to fundamentally break down text. Right? So the way we break down text is as follows. Okay. We have phonemes, we have morphemes and lexemes, we have syntax and context. So as you rise above here, okay, we eventually get our basic the most complicated form of text, which is something like a document or a novel or a research paper or something like that, right? But let's go slowly now. Like I said, words and sounds are extremely interconnected. So we have phonemes, right? The basic structure in natural language processing is the phoneme. So speech to text, speaker identification, text to speech, all of these fall under phonemes. And this entire area is studied in speech signal processing. And this is not relevant for us. However, right? It's important to understand this. For example, let me give you an idea. Okay, guys, what does this sound like? See, in generally, when we put C in a word, what is the sound that you can associate it with it? We can associate both sir and K both with this C, right? With C, do you guys agree? Yes or no? Sir, K, both sounds can be associated with this C. Okay? Yeah. But now if I put CH, what is this? Now we have K and Ch now, right? Suddenly we have K and Ch sounds, right? So this is what I mean by a phoneme. Okay? A phoneme is a smallest unit which represents sound. Okay, so that is basically what a phoneme is. If we take a lot of phonemes, yeah, English is a weird language. A lot of people are saying that. Yeah, I really wish we were studying in Hindi, right? Like if our forefathers had made different decisions, today everything would be in Hindi and we wouldn't have to run into so many problems. But that's okay. In fact, some NLP researchers have also said that Sanskrit is the best language for representation, right? It has absolutely no ambiguity. Whereas English is a language which has a lot of ambiguity, right? Which is what makes English natural language processing a little more difficult. But don't worry, right? We have figured out solutions. It's best to take what we have and move forward with it rather than worry about how things worked out, right? Okay, cool. So let's now focus on this. If I take together many phonemes and put them together, I get morphemes or lexemes. Okay. So let us now understand what are morphemes or lexemes. Morphemes are basically the smallest unit, right? The smallest unit which has some sort of meaning. For example, this pre. If I tell you the word pre, what do you guys understand generally? What do you guys usually understand? Before, right? So the word pre is an example of a morpheme. On its own, it's not a word, but it has some meaning associated with, right? So pre is one such word, and in is another word, right? Injustice or inflammable, inequality, stuff like that. In, un, these kinds of things. Yeah. So different types of suffixes and prefixes. These are essentially what come under morphemes and lexemes, right? So a lexeme, the difference between a morpheme and a lexeme is effectively, yeah. So a lexeme is something which finds similarity between things, right? So a morpheme is these things, these prefixes or suffixes which make some sound and have some meaning associated with it. Lexeme is basically a different form of the same word, right? So uh, lexemes sort of take these words and use different structural these things to it. Like they add different structural contexts to it. So, for example, inflammable and highly flammable both mean the same thing, right? So the lexeme in is sort of related to almost a blank thing there, right? Because flammable and inflammable both mean the same thing. So a lexeme is like a variant of this phoneme, which leads to a similar or a different meaning. So a lexeme is the written version of it, and broadly speaking, a morpheme is the smallest unit which holds some meaning, right? So essentially, it's that. Akshay's question to me is: are phonemes those words in a dictionary that teaches you how to pronounce a word? No, that is phonetics, right? That is phonetics. But you're right. Every phoneme in the English language will have some representation there, right? So in the dictionary, those characters that you see, right, that is known as the phonetic language. It sort of helps you pronounce these words. So yes. Okay. So once we have morphemes and lexemes, we essentially now put them all together to form phrases and sentences, right? So from morphemes and lexemes, we usually go to sort of gathering them together and then build syntax, right? And once we have syntax, right? Once we have phrases and sentences, like things like, so you can have phrases and sentences like, okay, let's take this one for example. That day he won. Okay, let's take a look at this example, right? So this is an example of a sentence where I'm putting together multiple words together to make some sense, right? What does this tell you basically? That on some day some guy won. Can you just quickly tell me, do you get a positive sentiment from Do you get a positive sentiment or negative sentiments from it? Abhijit has an amazing counter to that. He says today RCB will lose. Although I know it's although I know it's truth, but yeah. Okay. But yeah, for now, let's come back. That day he won, right? Does this sentence give you a positive or a negative feel? Can you hit yes if this gives you a positive connotation, and no if it gives you a negative connotation? Yeah. Okay. Let me give you an example of context, right? So I constructed this for a specific reason. Usually, right? Okay. Yes. No from his rival. Exactly. Yeah. Okay. Cool. So now, if I take this one little bit of sentence here, right? If I take this one little bit of sentence here and I put it before this, now does this change for you? He usually lost to make her feel better. That day he won, right? Now it sounds like he was angry for some reason that day, and though usually he lost to probably keep the heart of his daughter, he won. He decided to win that day because he didn't care, right? So now suddenly this has a negative context, right? So broadly speaking, so guys, do you agree? Now with this extra sentence here, it's now negative. At least the people who said yes before, I hope you agree now, right? Okay, this has a negative connotation. Okay, so guys, this is basically why speech or natural language in general is difficult to deal with. Why is it difficult to deal with? Because more than any of these, right? Phonemes, morphemes, lexemes, syntax, all of this is okay. But the true meaning behind these words is based on the context, right? So context is king. We saw that context was king even in the case of image processing, right? We saw that we had to build this convolution operator so that we can keep the contextual information in the image intact. Here it is even more obvious. Reading a sentence on its own may not give you the meaning unless you put it in the right context, right? So natural language processing on the whole is sort of more context dependent than our uh, image processing was, or computer vision was, right? Okay. So this basically gives you an idea of how we build natural languages, right? If you had to think about how would you explain the architecture of this language, right? If we for a minute imagine that we have a compiler in our heads and we try and analyze what is it that that compiler is doing while it is interpreting these bodies of text, right? What you have to understand is these words on their own don't have much meaning, but the context is what decides most of the meaning, right? And that is why most of the important tasks in natural language processing requires some knowledge and some representation of this context, right? So now that we have understood how natural language is built, we will relate these things to the different types of tasks we generally do in natural language processing, right? So let's talk about that shortly. I'll quickly take up Akshay's comments. Can I say my sample space is modified? Context changed? Sample space, yes, right? So in probability theory, the sample space tells you the set of all possibilities, right? In the same way, the context tells you a sort of set of all possible outcomes, right? So a certain outcome can be good or bad based on the sample space that you start with, right? So in the same way, I agree. It is sort of related. Interestingly, once we go and see topic modeling, right, we will see probabilistic models such as these Markov chains and stuff like that, right? So in topic modeling, for example, we will see this more explicitly. What you said just now, I will actually bring it to probability terms and we'll discuss that, right? Okay. So Narendra says, in case of context, how is sarcasm detected by NLP? So Narendra, generally it is possible for an NLP to detect sarcasm. In fact, ChatGPT can probably do it, right? It is able to do it by figuring out contexts. So, okay, let's ask ourselves something. You guys remember computer vision image similarity search? You guys remember image similarity search based on that? Okay, cool. What was the basic idea over there? We took an image and we converted it to an embedding which has some information about the objects in that image, right? Which is why we were able to do similarity search, right? Yes, exactly. So the same idea kind of carries over to natural language processing, right? The core contextual information can be encoded in the form of certain vectors. And these vectors are known as embeddings. And these embeddings are what will help us arrive at this context. So, in principle, yes, it is possible for you to train a machine to understand sarcasm, because at the end of the day, if you specify the embedding properly, it will be able to understand it, right? It's extremely task dependent, right? In computer vision, the task was object classification, which forced the neural network to encode those object informations. Now we have to ask ourselves, what should I do for natural language so that that gets encoded, right? And I'm not going to give you the answer today. We're going to come to the answer soon, right? Okay, cool. Like Avijit says, yes, you can use the embeddings for k nearest neighbors and look for related concepts. So, for example, if the embedding of a certain sentence comes out on the negative side of things, you will sort of understand that it's NLP, although it has a lot of positive words, right? So, we will talk about how to achieve these low-level tasks soon. Specifically today, we're going to see one part of it, right, which is sentiment analysis. But let's get there naturally. Okay, we're still not done discussing the broad problems that we generally solve in natural language processing. So first, let's complete that discussion. Then we will move on to how to sort of encode words as vectors and different problems in natural language processing we're going to see, right? Okay. Now, for now, let us get an understanding of what are the broad problems which are possible over here. Okay. So when it comes down to phonemes, the broad problems that are associated with phonemes, at least, are speech to text identification, speaker identification, text to speech. All of these tasks are mainly signal processing tasks. It is not possible for me to discuss this with you unless you understand some very basic concepts such as discrete wavelet transform, or what is a spectrogram, or what is a time frequency representation. Unless you understand these terms, it's not possible to talk about this, right? So we're going to avoid this part, because anyway we're not interested in this part. We're more interested in the problems which come after this level, right? So the problems which come after this level is things like tokenization, word embeddings, POS tagging. POS tagging means parts of speech tagging. So you guys remember in 10th standard we used to have what is a noun, what is a verb, what is an adjective, right? So those noun, verb, adjective, those kinds of things are known as parts of speech. And if I give you a sentence and you can tell me what is the verb, what is the noun, what is the phrase, what is the idiom, all that stuff, then it is known as parts of speech tagging, right? Okay. Word embeddings are nothing but ways for you to sort of represent words in a certain meaningful context. So for example, you could have word embeddings for images, right? So if you write a program which can sort of annotate images, it would sort of require you to design a word embedding first. So that is what word embeddings are. Tokenization is basically breaking down a sentence into meaning, right? So you can do it with tokenization. We're going to see this shortly, so I'll not expand too much on this. Okay. So at the level of morphemes and lexemes, right? These are the problems that we can solve. At the level of syntax, that is at the level of phrases and sentences, the biggest success that we've had till date is this one, right? Entity extraction. So what is entity extraction? If I give you a document, can you give me something similar, right? What does this for us? What was the first thing which came out in 1999 and which is now a probably $1 trillion company? Google search, right? Of course. So Google search works at the level of phrases and sentences. It basically tries to see what is the similarity of your given input document. It tries to find the similar looking things overall in all the available web documents, and it returns results to you, right? Okay. So that happens at the level of syntax. You also have things like relation extraction. Like, let us say you want to take a piece of text and you want to build a concept graph. What do I mean by a concept graph? Basically some keywords in that text which are somehow interconnected to each other, right? So those kinds of things are known as relation extraction. Finally, you have parsing, right? Parsing is basically making sense of certain pieces of text. So again, this comes under syntax manipulation and things like that. Finally, the one which has caught our attention recently is context, right? Things like summarization, topic modeling, sentiment analysis, probably chatbots, or you know, uh, like interaction systems. These kinds of things fall under this level, right? So if you are dealing with So yeah, okay. So why did we discuss all this, right? Why did we discuss all this? We basically discussed all this to understand that the problem that you're trying to solve in natural language processing is very much related to the hierarchy of how these languages are built, right? That is the main thing, main takeaway that I want you guys to have. If you want to solve a certain problem here, you have to ask yourself which of these at which of these levels do I want my model to think, right? So you can have your models only think on some levels, or you might need your model to sort of have multiple layers, right? So that kind of understanding is what we're trying to build now. Okay, we're going to try and understand the difficulty of these, right? And we're going to see if there's any relationship between the difficulty and the structure, and usually we'll see that there is. So 99% of the time there is. Of course, it's easy to mess things up. But yeah, I'll just show you the hierarchy of tasks by difficulty in NLP, right? So these are the problems broadly that people try to solve. And we, at somewhere along the course, we're going to come across each and every one of these problems, right? We're going to try our best to come across each and every one of these problems. So let's see the hierarchy of difficulty. NLP hierarchy of difficulty, right? Okay, so this is what this is. Okay, so just give me one moment. I'll quickly take up the questions which have been asked. Bishal says, can I make use of something, read big reports and convert it into small summary? Yes, Bishal. You have these systems which are known as text summarization systems. There are some really good ones out there. Okay, Google has one of them. I don't remember the name, but I'll see if I can find the link and share it with you maybe next class or something. Essentially, it's possible. TLDR. Yeah. TLDR is the name of the model, I believe. Is it TLDR? I mean, it's TLDR stands for too long. So this is, yeah. TLDR this. Okay, perfect. I found the website which does this. I'll simply share this. Thanks a lot, Arun, for that. Okay, so guys, maybe you can check this out. Sean says, could you just explain in short again the difference between morphemes and lexemes? Sure. Just give me 1 second. I'll think of a better example. A morpheme is basically this thing. Okay, just give me one moment. I'll think of a good example. Right. So a morpheme is essentially the smallest unit that has meaning. It is formed by a combination of phonemes. Lexemes are structure variations of morphemes related to one another by meaning. Okay, fine. So let's look at it this way. Pre is a suffix which means right, something which means before. Is there any other suffix that we can use to say before? So I have pre and I have it's okay. Maybe this is not such a good example. So essentially it's like this, right? Okay, so I can give you an abstract understanding. You have X, Y, Z, which are all suffixes meaning the same thing, right? So individually, these are morphemes. But then the relationship between them is known as the lexeme. So you say that Y is a lexeme of X, or you say Z is a lexeme of Y. Now, unfortunately, a good example is not coming to me. Can we think of something? So let's say, okay, un, im, and dis. Okay, perfect. So you have un, I am, and dis, right? Yeah. Unexpected, no, wait, what? Disillusionment, unillusionment, no, that's not a good example. I know for a fact that there's a example where un and dis are both applicable, right? As distrust, mistrust, and miss is also there, right? Okay, so basically over here we say that un, im, dis, and miss are all so distrust and mistrust is there, right? So misinformation, disinformation, perfect. Unlike, dislike, yeah. Un and dis, unlike, dislike. Perfect, perfect. Thank you so much. I'm getting so many examples now. So we say that these are morphemes on their own, but then these are lexemes of each other because the fundamental meaning is the same, right? So lexeme defines the relationship between your morphemes, right? Is that clear now, Sean? Yeah. Yeah, incoming ing for prefix, right? Okay, I see. Yeah, that is what is morphemes. Yes, ing is the morpheme over there. The lexeme will be something which has similar meaning to that, right? So that would be a lexeme. Cool. Yeah. Okay. So coming back now, let's talk a little bit about the typical problems that we solve. And then once we discuss the hierarchy of problems, we're going to go ahead and we're going to talk about one such problem for today, right? Okay. So now let's talk about the hierarchy of difficulty. Of course, can you guys tell me for these three, right? Do you really need any knowledge of optimization or math? Or is it okay if we know coding? For these three: spell checking, keyword based information retrieval, topic modeling? No? Or we will need some sort of optimization? Really? Is it possible to sort of have a guy who's very good at computer algorithms solve these problems? Spell checking, come on, you have to tell me. You have to tell me that spell checking is easily solvable, right? Regex, right? So anyone who knows regex can sort of solve spell checking. Okay. Keyword based information retrieval is what Google does, right? You give a keyword, it looks for documents which have that keyword represented really well. Okay. So term frequency by inverse document frequency, that is what the page ranking algorithm is. That comes under keyword based information retrieval. Topic modeling is basically if I give you a document and I tell you to tell me the top 5 keywords in this document, don't you think all you have to do is look at the relative frequencies of all the words and then just the top 5 or top 6 frequency words? Yeah, count vectorizer can sort of do it for me, right? Yeah. So essentially, spell checking, keyword based information retrieval, and topic modeling are problems where the solutions are readily available in the form of very simple representation hacks. What do I mean by that? Spell checking, all you have to do is once someone starts typing, you have to go and index it in a dictionary. If it is not there in the dictionary, you have to find the closest word to it. So this is basically like k nearest neighbors on the dictionaries, right? That you build. So spell checking can sort of be very easily solved if you have a k nearest neighbor on a dictionary sort of representation. Keyword based information retrieval is basically for every document in your database, you will go and you will put a certain number over there. Okay, you're going to build a linked list for every document in your data structure, like in your database. You're going to go there and you're going to say, you're going to store the relationship of the keywords in that document to that document, right? You're going to basically count term frequency by inverse document frequency on that whole thing. That will basically give you the importance of certain words for those documents. So now if I say, give me all the documents you have which contain the keyword machine learning. So a system, a deterministic system is able to go back and retrieve all that information for you, right? So the point I'm trying to make here is the easy problems in natural language processing really don't require you to know a lot of optimization and machine learning in general. We have pretty decent solutions without using any sort of optimization. Do you guys agree or disagree? Anyone who disagrees with this statement, please let me know. It would be interesting. See, guys, again, I don't know everything. If you disagree and you have a different viewpoint, it's amazing to share it with the class, right? So please make sure you do that. Okay. So let me pause here. In the meantime, you guys can go through the other tasks that we do and try to guess what these are, right? Okay. Now let me quickly take up the comments which are there. Okay, so people were asking me what is topic modeling. I answered that. Spell checking and keywords based search is solvable, but for topic modeling and text classification, we can do it in rule based probably, but we will still need to word embeddings and add network to do the task. Yeah, I agree. So Sean, I totally, absolutely agree with you that it is possible to improve performance by using optimization here. The only point I'm trying to make here is, why am I classifying these problems as easy? Because a solution is readily available to a person who does not know about optimization, right? So from that point of view, solving these problems becomes kind of easy, right? Totally agree. It's always possible to get better performing algorithms if we know that stuff, but we don't need it. It's not required as such. So that's why these are relatively easy topics. Okay. So Narendra says how regex checks spellings not clear. Can you please elaborate? So Narendra, in a regular expression, right? I can, as you're typing, what I can do is I can sort of, okay, let me think about this. Yeah. So I can essentially build a very efficient representation, right? I can build a tokenizer, right? I can build a tokenizer which will build a very good index for my k nearest neighbor search, right? Do you understand? Do you understand this thing, what dictionaries are in Python, right? Yeah, yes, Biswarup. Grammarly does these parts. So you know what dictionaries are, right? Dictionaries are big O of one data structures. So if I want to build a good nearest neighbor search kind of thing, or a good sort of, what do you say? Um, a good hash function for spellings, right? In a dictionary, I will need to use something which is known as a tokenizer. So it will take different parts and it will map it to different regions in your database, right? So the process of building a sort of good spell checker will require knowledge in the areas of tokenization, compilers, like compiler building and stuff like that, right? So that is why I'm saying regex is sort of related to that. So regular expressions is something which helps you build a context-free grammar. Using that knowledge, you can sort of build a very efficient database. So it's not directly related, but it is sort of related in the task, right? So that's how I mean it. Uh, can Redis do this? Redis, as far as I believe, is a caching algorithm. It does hardware caching. If your dictionary is small enough to to fill inside a cache, then I believe Redis can do it. It's a matter of how big that dictionary is, right? So yeah, cool. So these are the first three kind of simple tasks. Okay, for a long time, people thought this was natural language processing, right? But again, as more problems came along, as technologies evolved, we started solving more and more uh, sort of complicated problems. So the first one, which sort of necessarily requires you knowledge of optimization theory, is this one, right? Text classification. So text classification is nothing but things like sentiment analysis. In fact, text classification is what is the problem we're going to solve today. Okay, today we're going to do Twitter sentiment analysis. Okay, and this comes under text classification, right? Okay, so this is one of the first problems here which require you to have knowledge of optimization, vectors, math, all that. Okay, now once you have that, you come to information extraction. What is information extraction? What do you think? What's your best guess? Okay. NER? Yeah. Named entity recognition can do information extraction. I completely agree, Amit. But what I'm actually talking about in over here is things like, let us say there's a structured document, right? Let us say there is an email. Will it be possible for you guys to write a simple program which tells you the from, the to, the date, and the body of the text and attachments? Do you think it's simple enough to do that? Yeah. So named entity, so information extraction comes in various forms. Okay, you can have information extraction for structured versus unstructured, right? What we are talking about here, okay, what we are talking about here is the unstructured part, right? For unstructured part, we definitely need to have some knowledge of uh, optimization and stuff like that, right? So we solve the unstructured information extraction problem using intelligent systems. So off-track email spam topic modeling. Yeah, yeah. Is email spam detection topic modeling? No, I would put email spam detection in text classification, Arun. I don't think it's easy to use topic modeling to say spam unless you want to build a very rudimentary system. I can think of a way to use topic modeling to do email spam. You can basically have a collection of words which tells you if that is a spam or not, but that's not how we generally solve it. We go for classification. So Sunny says resume tracking systems. Perfect. Yes. Right? Yeah. Avijit, naive Bayes is what we would normally use for text classification, but there are better ways of doing it. Today, we're going to explain a regression based way, right? Let's see how to do that. Okay. So we have this as one of the problems. So guys, only thing I want you to take away from this is information extraction. I want you to think of it as unstructured in the sense that the data from which you want to do information extraction is a text. Okay, that is what we mean by information extraction over here. Okay, now just one moment, let me answer Vishal's one question, then I will move ahead. Vishal says, let's say I have a PDF. Is there anything that summarizes the whole report? Yes, you can convert the PDF to text using a simple Python library. Then you can come to this website, right? You can come to this website called TLDR, right? This one, the one that I showed you. So you can use this now, and you can use, yeah. So it's quite easy. Okay, now let's go to the next one. This is what is of most interest to us, right? Closed domain conversational agent, right? What is the library? Vishal, I'll share it with you. I don't know it off the top of my head, but there is a Python library which helps you extract info from a PDF. I've used it before. I don't remember it. I'll get back to you. Okay. So closed domain conversational agent. Oh, by the way, Vishal, this is one of the questions you have to put in the questions tab. I'm sorry, I get distracted. Right? Yeah. Okay. So you have closed domain conversational agent. What is a closed domain conversational agent? Something like a helper on your website, chatbot, right? A very basic chatbot. So if you guys have used Swiggy in recent times, if you have an issue with your Swiggy, right, you can go to the chat section. Before it puts you to a human, right, it asks you a series of questions. So something which is trained to ask you a series of questions so that it's easier to assign a proper delivery agent to you. Something like that is a closed domain conversational agent. Yeah. So a closed domain. Why closed domain? Because the context it is able to handle is kind of limited. It's only able to do things within that context. It's not able to understand things like poetry or the meaning of life and stuff like that. For that, you'll have to go to ChatGPT, right? Which is open domain conversational agent. And that too, we're not sure if it's able to do it. We're just hypothesizing right now. Okay. Then once you have closed domain conversational agents, you can think of this as some sort of decision tree. We come to text summarization, where you have to actually understand the text and then bring it over, right? Yeah. So this is like a narrow AI chatbot, as Prasad says. Perfect, right? This is like a narrow AI chatbot. Then we come to text summarization. TLDR is the best example I can give you for this, right? So we've already talked about this. Next, let's go to question answering. Question answering is basically is a system. So why is question answering slightly more difficult than text summarization? Because now you have to not only understand what's important, you have to understand what's important in the correct context. So if you have been paying close attention, this is the first time context is coming into the picture, right? Context for the first time is coming into the picture here. It is not possible for you to do question answering properly unless you have trained a chatbot or a system to do context, right? Text summarization can be done without context. Closed, all of these tasks don't require context. This does. And as we see, as we're going to study, to build these kinds of systems, we fundamentally need to rethink how we are representing our text. Okay. So let's come back to this. During our 6th or 7th lecture, I believe. Right? Okay. Then we have machine translation. Machine translation is very simple. If I speak something in Hindi, you should have a machine which can translate it to English so that everyone can understand. Google Translate, exactly, right? Okay. So this is, broadly speaking, the hierarchy of problems that we generally want to solve in NLP. We saw that, broadly speaking, you have some problems which don't really require optimization and everything. You have some problems where optimization and everything is required, and you have some problems where you're not sure if optimization will even work in for sure or not, right? Only recently we have discovered that it's possible to do these tasks really, really well. Okay. After deep learning came into the picture, we've started doing these things well. Otherwise, before that, we were not able to. Okay. So this also gives us a certain hierarchy to the kinds of problems we can solve, right? So now let's talk about the approaches to problems. And you guys can tell me broadly, and you take any problem in the world, what are the approaches that we know? What is the first thing you do? What is the first thing you do? You guys remember hit and trial? You guys remember trial and error, brute force? Yeah. All of these mean the same thing, right? Brute force, trial and error, hit and try, shooting arrows in the dark, all of this, right? So the fancy word for all of this is this one, heuristics, right? Heuristics based approach is the first type that we have. Then we have essentially computer based solutions or hard coded solutions, right? And finally, we have machine learning solutions. So, broadly speaking, the approaches even in NLP are these, right? You have heuristics based approaches to solve problems, you have rule based approaches, and finally, you have optimization or learning, right? So, that's the idea. Cool. Assumptions in the sense that, okay, Sumit, can you please expand? What do you mean by assumptions? Are you asking me assumptions for what? Um, okay, I'll wait for you to respond. In the meantime, I'll take up Sean's comment. But text summarization would require to retain context of the sentences before summarizing it or creating a brief para for the same. So, Sean, broadly speaking, text summarization happens in multiple ways, right? You have, so I don't remember the exact terminology, but the simpler type of text summarization only requires you to pick the important sentences out. You don't really have to, uh, you don't really have to sort of keep the context information. It's possible for you to design an algorithm which will only pick out the most important sentences and put it in order so that the context is, yeah, huh. So the context, so that the context information is processed, right? Now you have another type of text summarization where it will understand the text and then produce something. But for that kind of approach, you will start coming it more like it will come more towards the hard side. So people have solved text summarization without context information, which is why I will put it above question answering. So that's the motivation why I said it that way, right? Okay. So assumptions to solving problems. Yeah. So assumption based approach, right? So that comes under rule based approach where we say, okay, this is a rule. If this rule is true, then what should I do, right? So assumption to solve problems would come under rule based approaches, right? Okay. So guys, to give you some context, what we're going to do today now is we're going to focus on the heuristic based approach. What we're going to do today is we're going to develop a heuristic based approach to solve Twitter sentiment analysis. Oops. Okay, that is broadly what we're going to do today. This is a logical time for a break. Do you guys want a break for 5 minutes? And once we come back from the break, we can get into the dirty details of this, right? Okay, so those of you who want a break, please hit yes. Those of you who don't, please hit no. Narendra is requesting for a 10-minute break. Guys, 10 minutes is too much. Please, can we keep it to 5? Otherwise, the length of the class will extend, right? I hope it's okay if I give you a 5-minute break. Yeah. This is not a negotiation, bro. This is class. Okay, fine. Since today is the first class, I'll settle for 7.5. But going forward, please remember my breaks are 5 minutes. Okay. Since it's just the first class. Yeah. Let's do 7:30. Oh wow, okay, no. 7 minutes and 30 seconds. You know what? I'll lead the 30 seconds on my side. I'm rounding down. I'm sorry. I'm very mean as a teacher. So I'm going to round down. I'm going to give you a 7 minute break. I'll see you guys in 7 minutes. Anyway, 30 seconds of bullshitting I did, no? So it covers up. See you guys in 7 minutes. And we're back. Some people are not back. Okay, cool. No one's back. Okay. Is this like the class is revolting? You're saying, no, we want our 30 seconds. Okay, I don't mind. I mean, I can tell you a joke in 30 seconds. I don't know. Like, do I know any good joke which I've heard in 30 seconds? Like recently, biggest joke I've heard is RCB may win. One of my friends is a hardcore RCB fan, so maybe that could be one of the good jokes that I've heard. But yeah, apart from that, so my favorite IPL team has to be Mumbai Indians. I'm basically so I was born and brought up in Thane, right? So Mumbai is kind of close to Thane. I grew up with a lot of people who were Mumbai Indians fans, so I'm also a bit of a Mumbai Indians fan. So yeah, yeah. At least hope is there. So let's live with that for a while. Okay, okay, cool, nice. Oh, people have lived in Thane before. Nice, good to know that. Okay, guys, I think that covers 30 seconds. I hope people enjoyed the 30 seconds extra. Now let's come back to topic. Right? Let's do what we're here for. Okay. So now what we're going to do is we're going to take up one problem in NLP. We're going to basically solve it using heuristics, right? We're going to see how well we do. And at the end of this, so the solution that I'm going to provide to you is kind of incomplete based on the knowledge that we have in CV and ML2, right? I want to see if you guys can come up with something better, right? But the main objective of this problem is to teach you some very common terms in natural language processing. We're going to understand things like uh, what's a regular expression. We're going to understand what's lemmatization stemming. We're going to try and understand different concepts. So as like in the recent syllabus, right, we have sort of introduced an intro to NLTK lecture. So have you guys gone through that? Introduction to NLTK. You guys have gone through it, right? Okay. So a lot of the concepts that we're going to study again, like we're going to do today, are also kind of related to that, right? So if you have not done it, guys, what I can do is I can give you access to my lecture when I took it. So if you guys are finding it difficult to understand some things today, what we can do is please reach out to me on Slack. I will make sure the lecture intro to NLTK is added to your dashboard, right? This is something that we do now, so please let me know. Okay, cool. Because there it's like a much more slow version of today's class. So what I'm going to do now is sort of rush through the steps. But if you find it difficult, please let me know. I will get that lecture added to your dashboard. Right? Okay. So let's discuss the problem. Our first NLP problem. Okay. And I'm pretty sure a lot of you guys have come across problems like this, right? So the problem is this, okay? We have a Twitter data set where we've basically collected a lot of data about people tweeting about COVID, okay? COVID-19. Okay. So essentially, when COVID-19 first hit the United States, right? Like when it started becoming hyped over there, people started tweeting about various problems that were happening, right? So you guys may have heard of people who are holding toilet paper rolls, people who are holding sanitizers. Like the demand for sanitizers, toilet paper, all these basic necessities started increasing so much that people were not able to buy them, right? And it became like a commodity in those times. So what what the way these problems were detected was by looking at the Twitter feed of these people, right? So essentially our objective is to do sentiment analysis on COVID-19 tweets. Okay, broadly speaking, we have two sentiments, right? We have positive sentiments and negative sentiments. So what we have to do is we have to see, so what we have in our hand is a data set where all these where we have these labels present. We have to, for unseen data, we have to label them as either positive or negative. Okay, so without further ado, let's get started. Let's come to our code. first thing I'm going to do is, of course, I'm going to install all the required libraries. One thing that you guys have to know about Google Chrome is, Google Colab is, it does not give you NLTK by default. You have to separately set it up using this pip install. Okay, so yeah, this is what I'm going to do first. Then I'm going to download my data. Okay, over here, and we're going to see what this data basically looks like. In the meantime, I'm going to quickly see if there are any comments. Yeah, Arun says sanitizers and masks were also, commodities in huge demand at that time. I agree. Right? In fact, in India, we had that, right? We had a huge shortage of sanitizers and masks. Luckily, we don't use toilet paper, so our problems were more manageable. Yeah. So we started using soaps instead of sanitizers, and our mother's dupatta instead of masks. So that we had that taken care of. Okay, cool. So by now we have the data set to our this thing. Yeah. Okay. So data frame says pd.readcsv corona tweets. Let's see what all we have. Okay. So we have a username. This is just an index for the user. You have a screen name. So basically they have encoded that. They don't want to mess with privacy. So you have numbers instead of screen names. You have the location of the tweet. You have the date of the tweet. You have the original text in the tweet, right? And you have the sentiment. So if you guys notice, we actually have multiple sentiments over here. We don't just have a single sentiment, right? Let's see what all sentiments we have. So first thing I'm going to do is I'm going to look at the sentiment column, and I'm going to draw a pie chart of what are the different types of sentiments we have in our data set. And this is the pie chart. Okay. So we have 27.4 extremely negative tweets, which is expected. Humans are generally pessimistic. You have 24.9% of positive tweets, which is great, which tells me that, okay, for all the pessimists, there are some optimists also. You have extremely positive tweets as well, right? That's very less compared to the extremely negative, but that's okay. You have neutral and negative tweets, right? Yeah. So Biswarup says, how is it classified already? So Biswarup, humans read these tweets and associated a sentiment score with it, right? So this is a labeled data set which is given to us. Now we have to build a classifier based on whatever we know to classify unseen tweets. Cool? That's the challenge for today. Okay. So this is what we have. What we have to do is very simple. We have to build a classifier. I think by now nobody's scared of the task of building classifier, right? You've seen ML methods, you've seen deep learning methods, you've seen NN methods. Classifier is like the easiest thing for us now, almost. So yeah, let's go ahead and discuss how we will build this. So first thing I'm going to do is I'm going to only keep the negative ones, right? Let's sort of see how many I have of only negative tweets. So I have 1041 only negative tweets. So the first thing I'm going to try doing is I'm going to build a balanced data set of positive and negative tweets. I'm going to sort of ignore the neutral, extremely negative, extremely positive. I'm going to try to just solve this problem by looking at the positive and the negatives for now. Okay. For now, we're going to look at this. We will discuss improvements and, probably things that we could have done differently at the end of the class. But for now, I want you to observe that what I'm doing is I'm basically taking all positive tweets as the subset of these tweets, subset of the rows where the sentiment is positive, okay? And the subset of the rows where the sentiment is negative, I'm calling it the all negative tweets. And if you notice, since there are 1041 of these, but there are only 947 of these, right? I'm going to limit it to the first 947. This is how I'm creating a balanced data set, right? Because generally it's a good idea to do that. Okay. So now I have my balanced data set. I'm going to apply the usual train test split to split it into positive and negative sets, right? Positive train, positive test, negative train, negative test. So I have two different data sets for training and testing. And we're going to be doing validation on this, right? Why? Because we want to see if our model has actually learned something or not. We don't just want to build a model which works for our training data set. We want it to work for everything. So we're going to do that now. Let's quickly print the size of the training data and some example tweets, right? Okay. So now let us see what we mean by positive tweets. Garlic price is set to go up since it's been confirmed that garlic will be working well against COVID-19. Use it plenty use it in plenty, please, if you can. So this tweet sort of has some information which may be useful to people, right? Which is why it was classified as a positive tweet. And if you notice, we have this hashtag coronavirus over here. Okay. The negative tweet is over here. She's the COVID-19 self-isolation queen, more toilet paper in her hands than I've ever seen. Oh my God, okay. It's like a proper rap song, right? So this is like a rap song which is, oh, you can't read this? Guys, is this visible? Is this better if I zoom in, Teja? Okay. Okay, awesome. Cool. Sorry about that. So, okay, hopefully, let me do one thing. Let me increase the size of this, right? Is this comfortable for everyone now? Okay, cool. Okay, because of color. Okay, fine. No worries. Okay. So this is a positive tweet. What I want you to understand over here is what do they mean by positive and what is negative, right? A positive tweet is something which they consider helpful for people. A negative tweet is something which is making fun of the situation or which is probably generating more fear in people, right? So broadly speaking, the classification of sentiment here in this context is whether if someone reads it, are they going to be uh, positive about the whole situation or are they going to be more negative about it, right? That is the classification we have here. Okay. Now, how do we understand this tweet? So what is the first step that we do in computer vision, right? If you remember, the first thing that we probably do in computer vision is standardization, normalization, because the input images are essentially matrices, right? Is there any natural way for me to represent this also as a vector and this also as a vector? Is there any natural way for me to do that? What do you guys think? Yeah, vectorization is there, Avijit. I totally agree. But can you tell me, is it coming naturally in the sense that, see, for an image, it's very easy to understand that it's a matrix, right? In the sense that if you give me an image and you tell me this image has a height and width, I will not question you. But if you give me a tweet and you tell me has this tweet has a fixed length, right? I probably won't believe you, right? I probably won't believe you if the tweet has fixed length. So okay, Avijit's solution is break it into words, but even that's problematic, right, Avijit? Because what's limited in a tweet is the characters. We have 150 characters, but we don't really have fixed lengths, right? So what I'm trying to point out is, it's not in general easy to get fixed length vectors given a piece of text. So we have to go for strategies which first convert this piece of text into some sort of a vector or the other. Okay. Whenever we want to, yeah, whenever we want to sort of do any sort of natural language processing from today onwards, right? The first step you guys are going to ask me is, how am I converting my text into vectors? If you don't ask me this, you're not getting the point, right? Yeah. So we have to make row vectors in some way. So what we're now going to see is what is the process by which what is the general process people follow to convert this into words. Okay, that is what we're going to see. Okay, so that involves a certain number of steps. I'm going to try my best to be as detailed as possible, guys. But again, there's a trade-off between time and this thing, right? So if you don't understand the first time I'm explaining, please put up a question, okay, on the questions tab. Okay, cool. So now let's go ahead. So the first thing I'm going to do is I'm going to use regular expressions to sort of do things. So how many people are hearing the word regular expression for the first time today? And is there anyone in the audience? Guys, again, nothing to feel ashamed about. I know absolutely nothing about this thing, okay? Cricket and everything. You drop me in a conference of biologists, I'll have no idea what's happening. So if you don't know regex, please let me know, right? Okay. There are some people who don't know regex. Let me explain what regex is. Essentially, what regex is a way for us to define rules. Okay, Narendra has heard of it but never used it. All right, okay. So let's talk about this for a while. Regular expressions. Okay. Let's talk about this for a while. So guys, regular expressions is a concept which comes under computer science. Okay, it comes under the topic of this theory of computation. Compiler theory, theory of computation or compiler theory, all of these things. Okay. What is basically a regular expression? Okay. What is it? What is a regular expression? Okay. The answer is that it is a set of predefined rules about characters or text, okay, which help us, okay, which help us sort of cluster them into unnamed clusters. Okay. So you can, so for those of you who don't know what a regular expression is, if you know what a clustering algorithm is, you're sorted. Okay. If you know what a clustering algorithm is, you're sorted. A regular expression is like a rule set which computer scientists use to sort of cluster certain strings. Okay. So in on a computer, a word is stored as a string, right? So what a regular expression basically does is it will take the string that you give it will pass it through this regular expression, and this regular expression will tell you true or false. If it is true, this string belongs to the cluster. If it is false, this string does not belong to the cluster. Is this idea clear to everyone? What a regular expression is? That is what it is. Okay. Now, the main challenge in regular expressions is how to write it. Okay. So people say that it's easy to understand what a regular expression does, but it's very difficult to get it done. Right. So let me make your life very easy. There is this amazing website called regexr. Okay. There's this amazing website called regexr. We are going to, so from now on, if you ever have any doubt about what a regular expression is, right, you can go here, you can play around with this website, and you can sort of use this to build a regular expression, right? I'll give you a very simple example. It is possible for me to identify all the OTPs that I've ever given you, right? So let me say 1, 2, 3, 4, 5, 4, 5, 5, 4, 3. If I do 128.0.0.1 and 6, 7, 7, 5, 1, 3, 2, 4, then I'll put down my phone number in case. Yeah. Okay. So I have all of these numbers, right? Out of these, what is the rule for the OTPs that I generally give at the start of the class? What's the rule for the OTP? If I ask you which of these is most probable to be an OTP in one of Dhruv's classes, what will you say? 1 and 2? Okay. 1 and 2? What's the second? 5-digit? Guys, as far as I remember, I've always given you 4-digit OTPs. Okay. To the best of my knowledge, I have always used 4-digit OTPs. There are some classes where I come and ask you questions instead of OTPs. But for now, let us agree that it's 4 digits. Okay. But Teja, fine. I'll give it to you. 4 or 5 digits. We can have rules for both. Right. So now let me show you an example of a regular expression. A regular expression will allow me to highlight only the candidate OTPs. Okay. So if I do something like this, right? If I do something like, wait. Yeah. Okay. Hold on. If I do \d4, right? Followed by this thing, space, right? White space. So the white space one is no. \d4 will identify any four this thing, right? I also have to tell it that you have to have a word ending over here. So I forgot how to do that. So again, so what I like about this website, guys, is if you are, dollar is the one. Arun has told me dollar is the one. So this is the anchor for dollar. Okay, but no, that is word ending, right? So I'll want to put it at the word start. So it would be this. Okay. No, but then I have to qualify a space over here. Okay. This at the front and this at the end. Okay. Let's see. That's not true, right? The reason why this won't work is because this is not at the string start. So this is for string starts. What I want to do is I want to say that there's a space here. So the way for me to do that is use \s, right? Huh. So anything followed by space and anything before for with space, right? Okay. So now this is the only one over here, right? Okay. So there are many solutions here. 0 to 9, 4 to 7 are okay. Cool. So the reason why I wanted to show this example is as follows. Okay. So now I have defined a rule which says first look for space at the start, any kind of space, right? Backslash S stands for white space. Many matches any white space character. Backslash D4 basically matches 4 digits. Okay. This in brackets, when I write 4, right, it will basically take this identifier, right? This identifier, and it will match that to, it will count those many occurrences of this, right? So this backslash D means digit over here. This 4 means quantifier, match any 4 of the preceding tokens. And this backslash S is again white space, right? So what is nice about this website is it gives you an exact understanding of what is the regular expression that you're putting here. If you guys want to build a regular expression, you can use these references, right? You can sort of look at this references. You can look at the cheat sheet as well. The cheat sheet will give you a lot of things. So those of you who don't understand regular expressions and want to learn, this website is amazing. Okay. So I request you to look at that. If you want a more gentle introduction into regular expressions, contact me. I will get the class added to your dashboard, right? That way you can understand each and every component of this regular expression that I've built here. But broadly speaking, this is how regular expressions work. So if I wanted to now build a set of rules which help me identify all the OTPs I've given in class, this is the set of rules that I would use, right? Okay. So now what we're going to do is we're going to use regular expressions to extract certain patterns from the text that we're going to feed to it. Okay. We're going to extract some patterns. So those of you who know it, right? What is backslash W? For those of you who know it, Sunny, yes, regex is a package. It is independent. Yes, Sunny, you're absolutely right. We can use it in SQL, Python, Pandas. Yes, yes. So words, right? So Indradeep and Arun and Sunny all give me the answer that this backslash W means words. Now, when I put this backslash W and put it in this bracket, right? If I put it in this bracket and then I put a plus, what this will basically do is it will count one or more words in my this thing. So now if I use this now, basically what it will do is it will use this rule to give me all possible words over here. Okay. So one moment, my bad. I forgot to extract a tweet and then do this. Let me quickly do that. First, let's extract a tweet. If I did not want to use a regular expression, how would I do it? I would simply apply the dot split operation on my sentence, right? So if I take one of these tweets and I want to sort of figure out what are the individual words inside this tweet, there are two methods I can use. I can use Python's dot split method, which is there for strings. Okay, what this will do is basically it will identify all the spaces in my text and it will basically separate using spaces. It is going to separate this into a list of words, right? Using the regular expression, this is what we get. I want you guys to pay careful attention to this and tell me where one thing is different from the other. Do you guys notice some text over here which is different? Yeah, there's a URL in the split way, right? So if you notice, the first answer is with split, the other one is with regex. So when we are doing splitting based on spaces, there are two problems here. First of all, there are punctuation marks which start appearing. There are these URLs which sort of start appearing. There are these hashtags which are there, right? So what is nice about the regex over here? What is nice about the regex method to use to split our text into different words is that URL text and hashtags, right? They get pre-processed properly. Generally, when we're reading a tweet, do we want to pay attention to the hash or do we want to pay attention to the text after the hash? We usually want to pay attention to the text after the tag, which is why we would prefer the regex way of doing it. right? So from now on, I want you guys to remember regex is a way for me to do intelligent processing on the string data that I have. This is one of the most low level operations, and you can sort of play around with this using this website. Okay, cool. So now that we have learned how to extract different words from our text, right? The question is, can we now consider this after applying regex on this text, right? Can we consider this as the vector of words, or do we have to go for something else, right? Again, we run into one problem if we just use this as our vector, right? The problem is we can have a lot of useless words. So with the useless words in our this thing are known as stop words, right? Okay, so let's sort of do that. So now what we're going to do is we're also going to see how we can get rid of the unnecessary words which are there here. For example, words like to, words like words like to, co, https, these kinds of things we can imagine they'll come a lot, right? So what we can do is we can sort of eliminate these words which we don't want to associate any meaning with, and we can remove them. So how do I do that, right? I can remove that by applying something which is known as stemming or lemmatization, right? Okay, so let's sort of go ahead and do that first. So first of all, there is one concept I want to introduce before I move on to that. The concept is that of word tokenizer and tweet tokenizer. Okay, so guys, this process of breaking down a tweet into its component words is known as tokenization. Okay, so let me make a this thing. So the application of this regular expression is tokenization. And what tokenization is the process of extracting words, individual words from a tweet. Okay, so there are people who build who use regex to build really complicated programs which can take care of edge cases like getting rid of these hyperlinks, getting rid like translating this hashtag to its root word, things like that, right? These can be taken care of using the NLTK library, using something which is known as a word tokenizer. So let me quickly show you the application of the word tokenizer before I proceed. Okay, so using NLTK. So the way I do it is I will simply say from NLTK.tokenize import word tokenize, right? And then I will say words equal to word tokenize of tweet. And using NLTK, these are the words that I have, right? So essentially, it has done a sort of smart job over here, but it has kept the hashes still, right? It has still kept the hashes as separate words. So to improve on that, we can use something which is known as a tweet tokenizer. Okay. So let me also do that. Let me use the tweet tokenizer and show you how that works. So, okay, just one moment. I need to see what exactly to import. Yeah, so nltk.tokenize import tweet tokenizer. So now I'm going to use tweet tokenizer instead of this. Okay, and let's sort of see how we can get the words out. Yeah. Oh, right. I have to apply word tweet tokenizer dot tokenize. Okay. Quickly do this. So create an object of this, and then I call the tokenized class of this, right? And this gives us our tweet tokenizer. So what's nice about the tweet tokenizer is it retains the hashtags over here, and it allows us to sort of maintain, or it allows us to maintain the information that this was a hashtag which was provided. The problem with the split sort of did it, but yeah, in general, it sort of makes sense to use a tokenizer because people who write these tokenizer classes usually put a lot of thought into what makes sense and what does not make sense, right? So in general, when we want to convert our text into individual words, the process we follow is to use a tokenizer, right? Okay. So now that this is sort of taken care of, let's move on. Uh, Let us sort of now figure out a way to get rid of all the hashtags and links, right? Okay. So to do that, what I'm going to be doing is I'm going to be running my own regular expressions to do that. So let's quickly see an example of that. So this is our tweets, all positive tweets. The 12th tweet in all our positive tweets is something which has these links, right? So what we're going to do is we're going to figure out how to remove these. All right. Okay, and let's see, right? So this is my original tweet. And once I have done that, once I have applied this, right? This is what I get. Consumers have increased their online shopping due to coronavirus. Retail e-commerce study coronavirus, right? Although these were like sort of hashtags and these were different links, this tokenizer basically allows us to essentially extract the individual meaningful words which is there in the tweet, right? So this is how we sort of do it. Over here, if you notice, this is the regular expression which is getting the old style retweets, and this is what gets rid of the hyperlinks, and this is what gets rid of the hash from the new type of tweets, right? Okay. So Akshay says, shouldn't we, instead of dropping hashtags, put them in a separate list? It makes sense to do that, Akshay. Definitely makes sense to do that. For today's application, we're not going to worry about that. We're going to try and get the hashtags as individual words. So what with the method we are going to use to encode this tweet, right, will require us to interpret the hashtags as meaningful words. So that is what we're going to do. Cool. So now effectively I have taken care of my tokenization. I've basically extracted all the meaningful words in my string. Now what I'm going to do is I'm going to do what Akshay was suggesting before, which is getting rid of stop words, then doing stemming and lemmatization, right? So let's quickly get through that process. So first I'm going to import all the English stop words. So guys, stop words are basically these words in a sentence which don't have individual meaning, right? So all the things like the, due to, all these kinds of things, right, are stop words. So there is NLTK is a Python library which stores a list of common stop words in English. Okay, so this is how you sort of download it and use it. So let's sort of see what the typical stop words are, right? So the typical stop words are I, me, myself, we, are, ours, ourselves, so on. So there's a huge list of these stop words. What we are going to do is we're going to write a simple piece of code which is essentially going to get rid of these stop words and punctuation parts. Okay, cool. So now let's do that. So I have this now. For word in, okay, tweet tokens is not defined. That's because I have not run this cell. Okay, quickly let me add this cell here and use it. Right, all this is doing is giving me my tokenized string. Then I run this to get all the stop words and the punctuation marks, and then we're going to sort of clean our data, right? So since now this is a list of words, all we have to do is remove things from here, from this list, if it is either in the stop words or if it's in the punctuation, right? So this is a simple list comprehension which allows us to do that, and we now have only the important words in this tweet. Okay, and now we're going to start analyzing whether the word has a positive or negative meaning at a word level, right? So now we have to sort of build a representation which tells us if the word itself is positive or negative, right? How can we do that? Is there any way for us to, in the most intuitive way possible, how do we sort of separate out the positive and negative words? Can we, so dictionary, sure, Arun, but don't you think we have something better than a dictionary? We have a labeled data set, right? We have a labeled data set. So we can sort of use we can sort of count repetitive words in negative tweets. We can count repetitive words in positive tweets, and we can sort of build a dictionary which tells us whether this word, how many times this word has appeared in a positive context, how many times this word has appeared in a negative context, right? We can sort of build a dictionary which tells us this. So let's go ahead and do that. Okay. So now, yeah, exactly. We are going to, so Sunny says this is like counting the conditional probability of word being positive. So actually it's the other way around, right? Conditional probability of positive given word. So we will be given one word. We have to tell what is the conditional probability of it being positive or negative. So now we're going to work towards building that. Okay. So let's go ahead and do that. So again, let me do one thing. For now, I'm going to skip the explanation of stemming and lemmatization. For those of you who don't know this, let me quickly explain what it is, and I'll come back to this, right? Okay. So I want you guys to understand stemming and lemmatization through this one simple figure first. Okay, let's understand stemming and lemmatization through this simple figure. Okay, so in this figure, what I want you guys to understand is all of these words, change, changing, changes, change, changer, all of these have a root word, right? And the root word here turns out to be chang, and this is stemming. Okay, the process of converting all the individual words into a single root word is known as stemming. The way stemming works is it looks at the actual characters present in the word to arrive at the root word, versus lemmatization, which basically tries to look at the semantic meaning of the word to arrive at the root word. So change, changing, changes, change, changer. So all of these ones, right? Changing, changes, change, changer, come from this base word change, right? So if you're using stemming to do this, you will end up with something like chang or chang, like it will drop the e over there. If you're using lemmatization to do this, it will basically arrive at the root word. So what you have to understand here is, first of all, what are these methods? These methods help us further reduce words to its root form. Why is that? Why is it necessary to do it? Let's think of this in terms of the conditional probability, right? So if I have change in one tweet and I have changed in another tweet, right? Do I want the count for change only to be updated, or do I want to keep change and change separate? What do you guys think? Which is better strategy? Don't you think it's better strategy to save the count of the positive or negative thing for just this one? It's better for change only, right? So that is why before we go for counting the frequencies, we have to make sure that we convert our words to a root form. Okay, that root form can be done using either of these methods. It's either stemming or lemmatization. Stemming is preferred when you have many words where you don't like stemming is preferred when you want words to go to their root form without keeping the meaning into consideration, right? Without taking the meaning into consideration. If you want to change it to root form, that is where you use stemming. Lemmatization will actually use the dictionary meaning. Okay, so both of these are methods which people developed using tools like regex. Okay, so somebody sat and wrote a huge list of regex expressions to actually do this, and the person who did this was this guy called Porter, right? Which is why we have Porter stemmer over here, right? So this is what we're going to now use. We're going to sort of convert this one tweet that we had, right, into its stemmed versions. So the stemmed versions are so consumers has gone to consum, increase has gone to increase without the e, and so on, right? Yeah. And Sean says stemming is also much faster than lemmatization. That is absolutely correct. In general, lemmatization takes more. Over here, we're going to go for stemming, right? And now we're going to put all the things that we have discussed so far into a single function so that we can repeat it for all the tweets in our data set, right? So we are going to do the following. First, we're going to remove the stock market tickers like $GE and all that. So basically, if you have these special characters, we're simply going to get rid of all of those special characters. Then we're going to remove the old style retweet. So if you have this RT anywhere in your text, right, it basically indicates that it's a retweet. So we're going to remove that next. Then we're going to sort of remove all the hyperlinks. So we have this regular expression which removes the hyperlinks. Then we're going to remove all the hashtags. Then we're going to apply a tokenizer on it, right? The tweet tokenizer, like I told you. And finally, we're going to remove the stop words and punctuations followed by stemming. Okay. So once all of this is done, we will get a tweets clean representation for our tweet. Okay. So this process effectively takes our tweet, keeps only the important words, the meaningful words. It gets rid of all the characters that we don't want. And it makes sure that when we are counting things, right, all the related words like change, changing, changes, change, changer, all these related words will get counted for the same value, right? We don't want different things for different forms of the word. So this is the motivation behind why we have constructed our preprocess method this way. Now, once we have created our preprocess method this way, we are simply going to apply it to this and see if we are getting the same thing, right? Okay. So all the things that we have done here effectively converts our tweet into these list of stemmed words, and this is what we have, right? Okay. Next, let us now figure out how to create a single feature out of this, right? The problem with all the list of words over here, like I said, is the length. There is no way for me to assure you that the length of all my tweets are going to be the same. So I will have to create some sort of features, right? I will have to create some sort of features. And as we know, it is easier to build a classifier if we have low dimensional features, right? Okay. So now let's talk about converting tweets to feature vectors. Okay, let's talk about converting tweets to feature vectors. Okay, so the way we are going to do this is we are going to define our feature vector as follows. My feature vector from now on is going to be the following. Okay, I'm going to have this one over here for a bias term. I'm going to have count positive, and I'm having count negative. Okay, so this is one of the dumbest ways I can ever build a feature vector for the process of sentiment classification. Why am I saying dumb? Because what are the assumptions that I'm making here, guys? I'm saying, so let me repeat whatever I've said. Okay, I'm saying that now that I have pre-processed my tweet over here, right? Now that I have pre-processed my tweet into this list of words, right? Into this list of words, what I'm going to do now is I'm going to count all the times each word occurred in a positive context. Then I'm going to count all the times these words appeared in a negative context. And for each tweet, I'm going to convert an X length vector. So all tweets have variable lengths. Right? All tweets have variable lengths. What I'm now going to do is I'm going to convert every tweet into this form. So what is the dimension of my vectors now for all my tweets, guys? What's the dimension of the vector? 3, right? So now once I do this, once I vectorize this, right? So the process of converting this into a vector is known as vectorization. Okay. Once I do this, once I take every tweet, convert it to this, it gets converted to an R3 vector. Okay. The entries over here are integers, if you notice. Okay. One is an integer, count positive is an integer, count negative is an integer. I have to make sure I convert it first to a floating type, a floating point data type if I'm applying some sort of learning algorithm on this, right? Okay. So let's keep that in mind and let's apply this transformation on all our tweets. Okay. So the way I'm going to do this is first I'm going to build a frequencies dictionary. Okay. So let's go through this really quick. So this build frequencies function over here is going to take all the tweets as input. It's going to take the labels also as input. So now I have my tweets over here. This is a list, by the way, and I have all the labels for my tweets over here. So what I'm going to do is first I'm going to say Y's list is np dot, yeah. So I'm essentially converting this to a list from a NumPy array. Then what I'm going to do is y comma tweet and zip ys dot tweets for word and process tweet. So I'm going to apply this pre-processing function on every input tweet that I have. Okay. Once I do that, I'm going to say pair equal to word comma y. Okay. Where y is the label. Okay. So what I want you to understand is now for every word, okay, for every word, I'm going to have a positive label if it has appeared in a positive context. I'm going to have word comma negative label if it appears in a negative context. So finally, in this dictionary freaks that I'm building, right, I'm going to have entries like this. Okay. So let us say, let's take an example over here. Let us say I have the word eats. Okay. In let us say first it appears in negative context. Let us say the count of this is 67. Okay. And then we have the word eats. Okay, actually I can't have the word eats, right? I can only have the word eat because after lemmatization it would have become eat. So my bad. This is eat. So I have eat comma 0, eat comma 1, colon 63. And then let me say I have a word like hell, which appears only in the negative context. Okay. So let us say there are 117 occurrences of the word hell, and let us say it appears only in the negative context. Then what you have to understand is this word hell won't have a positive number, right? So now essentially I'm going to build this frequency dictionary where I have a word, the context in which it appears, 0 means negative, 1 means positive. Okay. This is the context in which it appears, and these are the counts of these, right? Okay. So let's see how we're doing that. So in code, I'm saying pair equal to word comma y. If pair is already there in my dictionary, then I just add 1 to the count. If it is not there, then I'm going to say freaks of pairs equal to 1, right? So pretty straightforward code. Okay. So now I have this code, which is effectively converting my, which is effectively building a dictionary which counts the frequency of words which come in the positive and the negative contexts. Cool. Now, what I'm going to do is I'm going to apply this, right? I'm going to actually apply this. So this code cell now is effectively just going to create something which is known as training tweets. Then I'm going to run the build freaks on this training data, right? Okay. So let's run that. It will take a little bit of time. Let it complete. Okay. It has completed. I have this dictionary which now has 6920 word pairs, right? It has 6920 words along with the context in which it's appearing. Okay. So now let me again explain the feature that I want. Okay. Now I'm going to show you how to actually build this feature vector. So the way we build this feature vector is as follows. I have this freaks now, right? I have this FREQs. I'm defining my feature vector XM, which is the feature of tweet M, as 1 comma freaks of W comma 1. So this freaks of W comma 1 is simply going to give me the sum of positive frequencies, right? Because of how we have just defined this freaks dictionary. And this summation over freaks W comma 0 is going to give me the sum of all the negative, it's going to give me the sum of all the words which have appeared in the negative context over here, right? So effectively, this is how I'm building my dictionary here. This is how I'm building my feature vector here. Now, we simply have to convert all our data into this, right? So let's do that now. So this code cell effectively just goes through all the keys over here and it shows us the relative counts, right? Okay, 1 minute. Let's go through this. Keys are all of these. So effectively, it's showing me that the word void appeared in the positive context one time, and it appeared in the negative context 0 times. Then this word stop appeared in the positive way 14 times and 32 in the negative times. Right? Okay. So just one moment, I have a comment. In the case of multi-class, a number of features will be 1 plus number of classes, right? In case of multi-class, number of features will be 1 plus number of classes. Yes, you're right. In multi-class classification. So, but this is binary classification, right? We simply want to say positive or negative. So yeah, okay, cool. Okay, so now we're simply going to apply this, and we're going to sort of see words at this thing. So what I want you guys to understand is now each word is appearing as a positive as well as a negative, right? So if you want to sort of figure out whether a word has appeared mainly as a positive word or a mainly as a negative word, it's a good idea to probably use these two counts as the x comma y coordinates, right? We have to use this as the x comma y coordinates, and we have to see where it falls with respect to the y equal to x line. Okay, so let's do that and see. So this is the log of the negative counts. This is the log of the positive counts. Over here, we see that there are some words which are definitely more positive than negative, right? So in this plot, the words which are more positive than negative fall under this y equal to x line. The words which are more negative than positive go up, right? So you have things like sad, bad, mad, idea over here, which is more negative. Although I'm pretty sad, idea is on the negative side. Stop is there on the negative side. Your spirit on the negative side. Then you have all of these words like play, communication, or whatever, good, power. These are on the positive side of things. So now we have an understanding of where our words lie, right? Now comes the task of actually extracting this feature and doing something with it. So let me quickly add the code of feature extraction over here. So my feature extraction code is over here. It's simply a function which applies the preprocess tweet and the this function, right? Preprocess tweet and this frequencies thing. It applies that, and it gives you the feature corresponding to that. Okay. So this is what will do this part, where I take every tweet and convert it to this. Okay. Once I do that, let's see where we are. Right. So let's see one example of a training tweet. Okay, this is basically the tweet number 0. Once I take this, this is what the feature looks like. I have 1, comma 2.284 into 10 to the power 3 and 2.482 into 10 to the power 3. So this is 2284. This is 2482. Can you guys quickly tell me, is this more positive or more negative? I'll quickly show you what is the feature, right? So you have positive first and then negative. Is this more positive or more negative? Can you guys tell me? Okay. This is more negative, right? Because the later entry has more entries. So yeah, more negative. Cool. Okay. Now, now that we have done this, let us apply this function to all our data, right? This was an example. We're simply applying this function to one example to see how well it's doing. Now we'll apply it to everything in our data set, and let's see, right? Okay, cool. So now I have this very nice training data set, right? Everything that we have discussed up to this point was basically pre-processing to get to our typical machine learning problem state, right? What is the first thing required for a supervised learning task? It is this labeled data set, right? It's this xi comma yi, where I goes from 1 to n, right? So everything that we have discussed up to this point, guys, is basically stuff we needed to do to our data so that we can get it into this labeled form, right? So where my xi's are in rd and my yi's are in r, right? Here d is equal to 3 because I chose to extract 3 features per tweet. Okay, cool. Now can you guys tell me, do you know how to solve this problem? How do we now do analysis over here? How do we do sentiment analysis here? What are the techniques that you guys have learned? Okay, ANNs you've learned. What is the simplest one you've learned? Huh. Okay. What's the simplest one? DT? Okay, I don't see what DT is. Can you guys tell me what this thing is? Logistic regression is one thing. Decision trees, okay. NB, yeah, decision trees. Okay. DT is decision trees. Perfect. Yeah, decision trees can be applied, right? Okay. So now we have a host. Oh, NB is naive base. Okay. Cool. I get really thrown off by these abbreviations. I'm really sorry. Okay. So we have all of these, right? Okay. So now let's pick one method randomly and use it, and let's see where we get to, right? I'm picking logistic regression. Uh, I'm picking logistic regression. Let's just apply logistic regression and see if we can build a sort of predictor for what the label could be. Okay. And what do you guys expect? Do you think this is going to work well? Do you think? Can you guys predict? Okay. Here's the thing. Can you guys predict the accuracy? Let's take predictions. I want two numbers: prediction for training, average training accuracy, average test accuracy, and the winner will be the one who got it closest. Okay. So think about this. I have shown you what the data is. I want you guys to test. Avijit says 50% training classification accuracy and 40% test classification accuracy. I like, Avijit, the fact that you thought of the fact that testing will be much worse than training. So that's good. Okay. Fine. Tejas says 60-40, 70-65, 60-50. Let's see. Okay. Let's apply logistic regression. Let's see. Okay. Training accuracy came to 67%. Who got 67%? Arun got 70% training. Okay. So Arun is closest to this for now. Let's look at the test set accuracy as well. Right? Let's see if Arun got that right. So Arun is the winner when it comes to training accuracy, testing accuracy. Let's see. Yeah, 55%. Someone who said close to 55. Indradeep is the winner actually. Okay, cool. So when it comes to testing accuracy, Indradeep is the winner. Cool. But I really like the thought that you guys put into this, right? One thought process that all of you followed was my testing accuracy is probably going to be way worse than my training accuracy. Why was that? Can you tell me where I went wrong in my entire training pipeline? Can you identify the bug? Did I use my testing data set when I created this frequencies? Did I use that? Did I? Right? Yes or no? Have I used the testing data to create the frequencies? I have not. Right? So this entire thing was dependent on whether or not I'm including the testing tweets in this, right? So obviously this is not going to work well. So the best result we have now after applying logistic regression is this. We get a 55% accuracy and 67. Now I want you guys' opinion. Okay, I want you guys' opinion. Can you guys quickly tell me what should the baseline be over here? This is a binary classification problem. What's the baseline that you will expect? 50%? Yes. 50% is the baseline because by random choice, if you select one of the labels as this thing, that is our baseline model, right? So baseline is 50%. Our testing does only slightly better than 50%. So our overall method is not great. Okay. Just for completeness, let us get it to classify some tweets. Right? Okay. Thank God coronavirus is over. Seems like a positive tweet. Great. This is seriously ridiculous. Stop holding is 0. Government efforts are great is positive. Nonsense is 1. This is of course so this is just a single word nonsense which doesn't make any sense. So it's misclassified as a positive tweet. Panic buying is pushing up prices. Hashtag coronavirus is 0. Of course, a negative tweet. Thank you to make hand sanitizer in distillery amid outbreak, right? So this is a positive tweet. So broadly, we have built a system which is not working. What I want you guys help is what could we have done better? What could we have done better? And I want your suggestions. And I want you to give the one thing which could have made this better first, right? What is the core mistake that we made in converting our texts to vectors? Can you guys identify that? Do you guys agree that probably the core mistake we're making is this conversion process of to add these words to this vector? Sparsity, yes. So we have ignored, yes, yes. So one thing we could have done is we could have chosen a more sparse representation. We could have gone for sparse bag of words representation. Okay, bag of words representation, right? So why was, yeah, bag of words, right? So the problem here is, although we have classified at the word level, right? Although we have classified at the word level, okay, let's go back. Yeah, if we go back here, we have sort of classified things at this level, right? The main mistake we made was we probably want the syntax of the tweet to matter. We want the context information in this, right? So we probably wanted to do things at this level, but we got stuck over here, right? Typically, this form of debugging is what works in NLP. Okay, so in NLP, if you're getting worse performance than you have, the first thing that you have to look at to debug your model is go back here. Okay, the level at which we're operating is what has a problem. So that is what I agree is the worst thing that has happened here. Okay, what else? Let me go through this thing, right? So Indradeep suggests testing, right? Indradeep, do you mean to say test should have been used in frequencies, or do you think too less data is? Oh, okay. Oh, that was for something else. Oh, my bad. I'm sorry. Yeah, 50% benchmark. Okay, I'm sorry. I meant, yeah, got it. Okay. So Sunny says ignoring test input words. Testing input words. How will we ignore that? I didn't understand that strategy. Can you expand on that? Okay. Okay. The rest of you say more features and all that. Guys, what else could we have done better? Do you guys have no other idea? What else could we have done better? Any places where we may have had losses? I want your help in debugging, right? It sort of makes sense to. So if we are able to debug what went wrong today, we can motivate the topics which are forthcoming. So I want to see if I can motivate that. That's the main intention why I'm taking extra time to discuss this. So please bear with me. Yeah, in bag of words, but then we would have a lot of possible words and we have 3K tweets, right? I mean, dimension is much more than data point. Okay. So, Indradeep, you're right. But generally, when we build a bag of words model, right, we take certain steps to make sure it doesn't get too big. Okay. So, honestly speaking, the English dictionary has only about some 8 to 10,000 words. 8 to 10,000 length vectors are okay for us, generally, right? So, if you think about it, bag of words will have that length. Of course, whatever vector representation we do will be lesser than that, and it's okay for us. An image has way more, if you think about it, right? 600 cross 400 image is huge compared to this. So size and sparsity isn't something. They're problems, but they're not necessarily a bad thing, right? There are other ways of dealing with it. So, for example, you have these continuous bag of words representation, you have word to vec representations, we have embeddings. All of these things are there. All of these are valid options. Cool. So what we'll do is we'll see these different representations and their uses as the classes go along. But apart from this, what else is there? Vectorization can be improved. Okay, that is also this, right? So use alternative representations. I'll put it as a single thing. Okay. Vector, zers, embeddings, etc. And we'll slowly start studying these things. Anything else? Frequencies of words across tweets. Yeah, that is good. So, Anindya, if you think about it, right, this frequency actually does consider frequency of words across tweets. I guess what you mean is, okay. I guess what you mean, Anindya, is we should make sure that we sort of normalize it or something, right? I guess what you're telling me is probably our vector is huge, right? The size of these vectors is huge. If you look at it, each vector is an integer and it has huge values. Do you mean we have to normalize this? Okay, cool. So normalizing our vector representation, that could have some effect on this, right? This is one place where we should look at. Okay. I like Kamal's answer, guys. Kamal's answer is really nice. He says we could have we missed out on synonyms, right? So counts of synonym words. So if you think about it, this is the first suggestion I've got which says I don't have enough structure in my vector representation. So Kamal is basically telling me you're not uh, this thing. You're not basically you're taking word at the word level. You're not taking it at a meaning level, right? So we have not accounted for meaning. So let me put that down as the point. No semantic captured in the representation. Right? And finally, there's one point, unfortunately, which people have not given me. I'll just put it down. The major problem, right? The major problem is we have not used contextual information in any way. Okay. So we have not even thought about it. So this is kind of similar to this one and this one. So yeah. So essentially, what we have missed out on today is we have not exploited all the information that was present in our tweets. And broadly speaking, over the next 3 or 4 classes, we're going to explore different ways of solving the similar problem, like solving similar problems, which is text classification. We're going to explore how to do each of these things, almost each of these things, and that is the motivation that we're going to have for the forthcoming classes, right? Over time, we're going to now start improving our word representations in terms of sparsity. We're going to improve them in terms of the vector itself. We're going to improve it in terms of the meaning that it has, and we're also going to see how to factor in contextual information. So we're going to basically improve the level of our vector representation over the next few classes, and eventually we're going to hope we can build GPT like models, right? Let's get there logically. Okay. So guys, this sort of ends the content that I have for today's class. Thank you so much for being a wonderful audience. I'm going to be sharing this notebook along with the code that I have written. So I'm going to be sharing a detailed code. And as you guys requested, right? You guys wanted a single document which has the link to all the computer vision lectures, like the notebooks of the computer vision lectures. So I have sort of prepared this document. Okay. So this is a PDF which will have all the links. You just have to click on them and you can go there, right? So you can sort of use this. I'll be attaching it to today's lecture. Okay, cool. So nice. With that, I'm going to start the doubt session. I sincerely hope the person who asked the doubt out of turn stayed back. Let me check. His name started with a K, I believe. Yeah, no, looks like he left. So, okay. But I really wanted to take up his question. Let me go back up in chat and see if I can answer his question so that at least if he sees the class, he can get the answer, right? So, yeah. His doubt was related to computer vision and NLP rules. Like he had a doubt about a general question. I just wanted him to put it in the chat window, like in the questions tab, because it would have broken the flow. So but I want to give him an answer. So let me do that. Yeah. Oh, okay. He's here. Oh, damn. Sorry, Riju. I forgot your name. Okay, he put it. Okay, I'll answer this now. So Riju's question is, I'm working as an advanced driver assistance system department in a company as a data scientist. Okay. Driver assistance system. Okay. So you can tell me what is the scope of data scientist as compared to deep learning engineer in the CV field? Okay, cool. So I want to answer this question. Let's answer that. Okay. Right. So this is a driver assistance system, right? So the problem that your company is trying to solve is driver assistance. So I know this one company called Light Metrics which does this. The products that they have, okay, the products that are there at Light Metrics are things like driver drowsiness detection, right? You have road monitoring, road actions monitoring, right? You have trip monitoring, okay? So first question to you, Riju, are these the typical problems you solve at the company? By drowsiness, I mean you have to take a photo of the guy. You have to see if he's falling asleep, right? You have to constantly monitor the eyelids of the guy. So you have to build a system which can basically predict if the guy's eyes are shut or not. Road actions monitoring means how fast is this guy going on a certain road with respect to the rules of that road, right? So you need to know things like the GPS position of the vehicle, the road on which it's traveling, the rules for that. So all of this is usually available on a map system like OSRM, right? Open Street Maps. And then you have trip monitoring in the sense that has this driver taken the most efficient route to get there? Were there some distractions? Were there some unnecessary stops? Were there some incidents along that? So is this what you're talking about, first of all? Am I guessing this right? Active safety. Okay, that's also there, right? Okay. So we have pedestrian detection, emergency vehicle detection, free space detection, general problem. Okay, cool. So a lot of what you do is related to road actions, right? So basically things like pedestrians, emergency vehicles. So vehicles which are basically traveling towards you at a fast rate or something, right? Okay. And free space. By free space, I think you mean tailgating, right? Means is my car traveling so fast that it will dash somebody else? That is the tailgating problem. So okay. So now that I've understood what your company does, let me see your question. Can you tell me what is the scope as a scope of data scientist as compared to deep learning engineer in this CV field, right? So Riju, the point is this, okay? All of these algorithms, right? The state of the art which solve all of these problems are right now deep learning based. Okay. So a data scientist is someone who could I'll explain to you how Scalar thinks about these roles. Okay. A data analyst is a person who has domain knowledge and mathematics and statistics skills so that he or she can solve problems in the domain using these tools, right? That is what a data analyst is. A data scientist is somebody who knows enough coding, like who knows enough data structures and algorithms to apply an elegant coding solution to automate a problem, right? And a deep learning engineer um, is a special case of a data scientist. So it's a subset of data scientist where the deep learning engineer knows how to apply deep learning solutions to this, right? So that is what I understand as a deep learning guy. Okay. I would say in this field, a deep learning guy is more likely to survive because pedestrian detection is nothing but object detection, which we learned in CV, right? This is nothing but object detection. The state of the art right now for object detection is the YOLO V8. Okay. YOLO V5, YOLO V8, one of the YOLO families. These are the fastest ones. They can actually do it in real time. And if you're in a car, right, and you want to stop in time so that a pedestrian is not hit, you generally want to do this at a very fast frame rate. Okay. The state of the art algorithms which do this are YOLOs. They achieve a frame rate of around 75 frames per second, right? We saw this in our object detection 2 class. Emergency vehicles also same idea, right? You want to get an estimate of where the closest vehicle is. You want to be able to stop when the vehicle is a certain distance away from you based on the current speed that you have, based on this thing, right? Yeah. Oh wow, okay. Riju says we use lower YOLO model because embedding space issue. What is the embedding space issue? Okay, the higher YOLO models increase the embedding a lot, is it? Okay. Yeah. So what I would say is, yeah, and then this thing like free space, right? Free space detection is also a feature of object detection. So broadly speaking, YOLO is doing all the heavy lifting here, right? So now let us say that your company gets a competitor real soon, okay? And the only way to beat them is to sort of make your product faster or more reliable, right? Do you think you have the skills to improve the reliability and the speed of your model? Do you have those skills? if you have those skills, you can survive in this field, right? That is what we define as a deep learning engineer. A deep learning engineer is a person who knows uh, how to improve the stability, how to improve the consistency, how to improve the speed, the size, play around with these things, right? And there are various concepts which can be used to do this. So one cheap example I can give you is, if you want to make your thing consume less memory, you might want to consider something like knowledge distillation. So knowledge distillation is a process of training a student network which is smaller than your teacher network, right? So it will occupy less memory. It may not do too much in terms of speed, but it will definitely occupy lesser memory. So that is how you solve that problem, right? So in this computer vision field, what I would say is a deep learning engineer would have a higher chance of surviving than a normal data scientist, right? Yeah. Okay, you have to embed them in hardware, right? Yes, Riju. So now, okay. So Riju, you're actually telling me that space is a problem, right, for your YOLO model. So what you could do is you can use a higher YOLO model, which does, uh, which sort of, you can use a higher YOLO model through knowledge distillation. So sometimes what happens is, if you do knowledge distillation correctly, right, the trade-off between size and the accuracy, you can achieve really good trade-offs. Okay, so I'll suggest one library to you. There is something which is known as the knowledge distillation library in Python. So it's known as KD library, knowledge distillation library. I want you to probably go through this. So one way you can add value to your company is you can simply take this library, run it on your existing YOLO pre-trained model, and try to get that right. Maybe you guys have tried it. I don't know. I'm just guessing. But yeah, so that's the answer, right? To solve these kinds of problems, because the state of the art is deep learning based, it's important for us to train ourselves to be good deep learning engineers. A good deep learning engineer knows how to solve the following problems: how to make my model smaller, faster, more consistent, more reliable, right? All these things. By consistency, I mean true positive rate, false positive rate. By reliability, I mean overall accuracy, right? So that's the idea. So cool. I hope that answers your question. But in most of the cases, the architecture is already built. Yes, I agree. The architecture is built, but most of us do what you mostly do is fine tune, right? But to know what is the best way to fine tune, right, you need to be updated with the most recent literature. So, for example, what if last year you're using last year's method, but this year's method does it 2 times better? And the way research is going in this field right now, it is actually moving that fast. It is highly possible that if somebody has gotten an X delta, guys will come up with a 2x or 3x delta within a few years, right? So that is why I'm saying it is very important for a deep learning engineer to be aware of what is the state of the art in the literature and propose what is the um, most recent state of the art, right? So that's the idea. So all I'm saying is, because this area is changing so fast, keeping yourself updated is what defines how good you are. If you have the correct mentality and the tools to keep yourself updated, by tools I mean if you know basic math, if you can understand research papers easily when you're reading them the first time, things like that, right? So those are the tools that you need to survive. So yeah, that's kind of what we need. So I hope that answers your question. Yeah, cool. You're welcome, Riju. I actually love this field, so I'll be more than happy to uh, answer these kinds of questions. Oh, Sean has another suggestion. He says quantization can also help. That's absolutely true. So there are typically 3 ways of reducing the size of your model, right? One is knowledge distillation, quantization, and pruning. Like these are the 3 methods you can use to reduce the size of your model, given that you have already pre-trained it. So now you can go for all of the 3 and pick the method which gives you the best trade-off between size and performance, right? So yeah. Now Mohan's question is, how is job market for data science or MLE roles right now? I'm not able to find data science jobs, even from scale-up replacements. Did not get any interview call. Mohan, you're looking at the wrong places. Currently, the best companies for MLE and deep learning engineer roles are startups. Okay, big companies are not taking those kinds of bets right now. There's a probably a hiring freeze in most of the big companies which are there, like Microsoft, Google, Facebook. All of these have hiring freezes at a high level. So the companies which are really aggressively hiring MLEs and deep learning engineers are startups. So my suggestion is maybe go to this website called Wellfound. So wellfound.com is basically what used to be Angel List about 5 to 10 years back. They are basically a list of all the startups in India. What's nice about this website is if you put in your details properly, right? They will give you everything. Like they'll be very transparent. They'll tell you what the expected salary range is. They'll be clear about what the requirements are. So the website as a whole is a very good source. So I would recommend that you try Wellfound. If you want to try, like it's kind of less likely, but there's also this website called Turing.com, which gives you remote jobs in the US for these roles, right? They might slightly pay better. So you can try both of these places. So the market is mainly in startup area. That's the final answer. Yeah, Turing is good. Okay, so you can try Turing, Mohan. You can try Turing. So Riju says quantization is already considered. Generally, all the C++ code use TF-Lite extension to predict. Okay, interesting. I have not actually worked with TF-Lite, Riju. I have never done that, so I might have to look into that. I understand what it is at a top level, but I haven't actually done the coding. So, yeah. Cool, guys. Any other questions? I'll be more than happy to take any doubts or concerns that you may have. If not, we can end the class in a couple of minutes. I hope you enjoyed your first lecture in NLP. But yeah, cool. Okay, guys. Good night. Thank you so much for being an amazing audience. And I will see you on Wednesday. We will be discussing. Wait, I'll tell you what we'll be discussing. We'll be discussing different representations for text. So basically, stuff like, word to vec and stuff. Is word to vec in this lecture? Let me just see. Yeah. So different. We're not yet going to. So we're not yet going to deep learning based solutions. We're still looking at heuristics next class. So we'll be doing things like TF, IDF, cosine similarity, PCA, L1, L2, all those kinds of things. So basically, other heuristic approaches. Cool. So see you guys next time. So Aditya says, Dhruv, can you get the NLTK lecture added? Sure, Aditya. Can you please ping me on Slack so that I remember? Because it will be very difficult for me to remember now. So if you ping me on Slack, I'll get it done. Okay. And one more thing is, Aditya, you'll have to raise a support ticket. From my end, what I can do is I can expedite the support ticket. So generally what happens is the ops team requests me to ask the students to raise a support ticket. So the fastest way to get these lectures added is raise a support ticket, send me the picture or send me the support ticket ID on Slack, and I can get that expedited. So yeah, cool. See you guys. Good night.